Hello, I'm Sung Yoon. Today I will talk about the texture mapping. These are the today class objectives. We will talk about the overview of the texture mapping, which is one of the very important concept in the rasterization, also the computer graphics. And when you perform the texture mapping, there are two main texture filtering issues. So we'll talk about them. And also, the last time we talked about the phone illumination, you may remember that phone illumination consists of the ambient, diffuse, also these non-ideal reflectors. So along that line, also we talked about the specular tone, and we also discussed a few shading techniques. One of your question, one of your fellow students mentioned about this one in the BRDF. For example, if the material is transparent, then the pi r, I guess. I mean the last we showed this the BRDF figure in the last time, and then he or she asked that this in the case of the transparent material, then this outgoing angle maybe more than over this 90 degree. In other words, passing through this boundary of the surface. Yeah, that's correct. So basically, I also got this figure from the wiki. In the case of the BRDF, so here we assume that non-transparent object, in other words, opaque material. Then once we hitting the photon, then the surface actually reflecting this photon in the all possible. It can reflect into the other spaces, right? So it's basically BRDF wanting to capture this one. But in the case of transparent model, for example, the human skin or the soft or the lips, then once the photon actually hitting there, and then some of photon actually penetrating some of the surface, and then actually it also do some sort of it actually travel within this material internal structure of the material, right? So you can see that you're hitting there and then traveling here and so on, and then it might emit, the photon may emit in another location and in some in that direction, right? So basically, you can see that what he or she asked is what he or she actually observed is correct, and then in this case actually the photon actually the emitting location may even different from the entering location. So basically there are many other issues that we need to consider. So there's actually the BSSRDF concept, which is actually the design which is designed for this kind of explain this kind of transparent objects for the appearance one. So if you're interested, you can look up the BSSRDF, also Google. Also you can also get some of concept in my book actually. So there are a lot of representing this kind of appearance model of transparent or translucent materials. Actually, they're difficult supporting this one. Also, it takes a lot of time. So one of the rendering technique for this kind of complex model is also the ray tracing. Actually, one can also use the rasterization technique for supporting this one, but also they require a lot of the very complicated operations. But once you can do that, the main idea of the rasterization is that we wanted to support that effect in an efficient way by utilizing this GPU. So there are very different rendering techniques. One approach is based on the rasterizations. Rasterization concept that we talked about in the class to accelerate this process, but there are actually some of the issues when you apply the rasterization, mainly because the real physics not really based on the rasterization concept. But later on we'll talk about ray tracing, which is actually very naturally applicable to the support with BRDF and even the BSSRDF. Thanks for bringing up this question. Now let's talk about the texture mapping. So if you look at the recent games and movies, it's very common to use the very complicated geometry or the very realistic appearance model. I mean, in other words, realistic look, right? So to support this kind of the realistic appearance model, then one can use a lot of triangles, right? But they're just using a lot of triangles with this associated color takes a lot of time for the model this kind of scene for the designer, right? But early on, so we can actually early on we wanted to support this kind of realistic appearance model, but basically it's very easy to draw this kind of the realistic look or capture this kind of look within the 2D image. That's the main idea of the using the texture mapping. Somehow we capture this kind of realistic appearance in the 2D map, and then using that map for rasterizing the triangle. So in other words, the basic main idea of texture mapping is that we want to add the details with these image representations. So here, this is actually the one in the main motivation for computer graphics is that we want to achieve the realistic look, right? So initially we actually start with some sort of triangle, right? And then so far we talked about the illumination model and shading model so that we can consider light, right? Now we wanted to we can capture the photo of the hippo, and then also we can also draw the realistic look of this animal, right? And then we adding that we represent them as a text 2D map, in other words texture map, and then we consider that realistic appearance color model when we rasterizing the triangle while considering light, also this texture map. So that way we can get a very realistic look here, as shown here. Also for example, this also I'm showing one level deeper the details here. So suppose that we want to actually visualize and render this kind of virtual character, right? And then suppose that this virtual character may consist of this kind of triangle, right? And then when you rasterize this triangle, so we somehow using the 2D map here. In other words, this texture map. So here it's much more easier to draw this kind of detail in the 2D over drawing the detail in the 3D, right? Actually, there are a lot of research going on for drawing the details on the 3D space, but it is much more natural to draw the details in this 2D image, right? And then so somehow we actually set up the mapping between this triangle, basically this triangle in the 3D mapping to this region in the texture map. And then when we rasterize this triangle, we get the color. I mean, before we mainly we actually compute the color from the vertex. I mean, the color information associated the vertex, right? And then sometimes we may interpolate those colors, right? But in this case, we can get we set up the mapping between this texture map, this regional texture map, and here. And then when you rasterize this triangle, we can get some color information from there. And then we get the more detailed color information. And then we consider we perform the illumination, and then we can perform this kind of operation. Also, you may remember that when I explained the phone illumination, there are many the constant factor like KD, KS, some sort of material dependent one, right? Also, we can also design the additional texture map 2D image that containing some sort of material dependent information for each within this 2D map. So we can actually provide that kind of information with the separate 2D map. So as you can see that there are many applications of using this 2D map, texture map, for different components of the actual rendering. I will get back to that one later on. But here I will talk about the main concept of texture mapping. Somehow we set up the mapping between this 2D, the texture, the triangle, and then when you're rasterizing the triangle, we get the color from there. So here, this is actually common texture mapping that we use in the OpenGL. So suppose that I have this 2D map, and then I want to actually, when you draw the triangle, or in this case I draw this quad, the rectangular shape, and then I want actually I want to get the color of the the rectangular shape from this texture map 2D map, right? And then to do that, I can use this one. So there's first of all, I need to here actually I didn't talk about all the details. Somehow I actually have this texture map, and then I actually bind. In other words, I actually let the OpenGL know that I'm going to use this texture. In other words, I bind the texture to the rasterization process, and then actually I use this 2D texture with this texture ID. And then here I draw this polygon, right? And then as usual, we use the GL vertex here, -1, -1. So you can say that these 4 vertex are specifying these 4 different vertex, right? And then as you can see in front of the specifying each vertex, you can see those there are texture coordinate, right? 0 to 1, 1, 1, and so on, right? So in other words, for example, for this one, -1, -1, this should be here, and then for this one, I use the texture coordinate of the 0 and 1, something like that, and so on. So somehow I actually associate. So you can see that this actually conceptually for each vertex location. Also, I attached the texture coordinate. The texture coordinate usually spans from the 0 to 1, 0 to 1. And then, so that's why actually I used something like the 0, some value from the 0 to 1 here. And then, we actually, as you can see here, for each vertex, we link some of the texture coordinate, right? And then, I think I should do it. But this texture map is just image, right? And in other words, it might have some of the pixel, right? Pixel, and then so the pixel in the texture, actually we call it as a texel, and then texel index actually there can be computed by this width and height, actually nothing but width and height of this 2D map, and then for the UV, we typically I use the U and V to include the coordinate of coordinate of the texture coordinates along the U and V. You can see that actually this is mapping to the X and Y, and then by multiplying U along the S index here, it's a little complicated, but the S and T is the actual texture index, and then U and V is the coordinate of the texture coordinate, and then for computing the texture index, we just multiplying their texture coordinate with their in the case of X, we actually multiplying with the U and width. In this case, the width is the 256, then maybe the V, if you use the U as the 0, then the texture index may be the 0, and then we use this 1 for the U, and we might get the last index of along the width of the texture one. So you can see that actually based on very simple calculation, we can link the texture coordinate with this texture index. In other words, we can access texture value within this 2D texture map. So based this one, we can set up the link like this. For this vertex, we want to use this particular the texture value. For example, we can use for this one, I want to use let's say this 0.5 and 0.5 along this S and T. Then when since we set up this link here, we can know for each within in a particular location in the triangle, we can know what's actually we can know what are the textile mapping to there. So here actually we are constructing the mapping between the coordinate of the vertex with this texture coordinate. But there are some of the issues. Here I will talk about the graphing issue. So I said that usually the texture coordinate specified the 0 to 1, right? 0 to 1. So the 0 is mapping to along this S, 0 is mapping to there. And then this 1 is mapping to this here, here. And then sometimes actually we can use the sum of the texture coordinate, maybe smaller than 0 and smaller than 1. And then we can actually use these two different wrapping modes. This one is the GL clamp. In other words, suppose that you actually use the texture coordinate bigger than 1, let's say 2. Then in other words, we clamp these 2 into the maximum texture coordinate, let's say 1. Then as you can see, basically for texture coordinate out of the 1 is mapping to the last index, so you can see that it's the same color actually repeating here, right? So this actually the GL clamp. The other one is actually GL repeat. So for example, once we got the 1, then it actually make it as the 0. so that you can see that actually we actually repeating this texture again and again. So for example, this one, if you use the 2, and 2 is again mapping to the 0, so that the same pattern actually showing up there again and again. And then you can choose these two different options here. Also, there could be the many other options depending on your application. But the much more important issue is that the sampling issues. So suppose that somehow in the screen space here, I had a triangle, and then I actually projected this triangle into the screen space, and then this one actually mapping to the pixel in your screen space, and then I'm actually doing the rasterization here, right? Suppose that I want to rasterize this region, this particular region, right? But in this case, I mapped this the texture map to this triangle, right? And then conceptually, suppose that this rectangular shape in the screen space can mapping to the arbitrary region in the texture space, right? Texture space is nothing but 2D texture map that I talked about so far, right? And depending on depending on how you look at this model, right? This character, the pixel when you are rasterizing this triangle, but the pixel here can mapping to some of region in here, right? But it could be the arbitrary shape. So in this case, actually, the question is that for this one, conceptually, this rectangular pixel shape can mapping to some shape in the texture space, right? Then the question is that what are the color? I mean, there could be the multiple texture in this texture map, right? Then how can you compute the representative texture color for that particular pixel, right? You can see that there are some sort of, since we link this texture map with the triangle, depending on how you look at the triangle, actually, there are some sort of sampling issue. In other words, why I say sampling, I need to sample the texture, right? And then there could be the sampling issue. So let me give you more details about the sampling issue. Suppose that somehow in this case happened that when I magnify the triangle a lot, in other words, suppose that I'm zooming in the triangle a lot, So in other words, I zooming in the triangle a lot, and in some cases, suppose that this is actually your screen space, your window, and this is your pixel, and then somehow I zoom the triangle a lot, and then I might get the triangle like this, right? Somehow I have to draw the triangle in a very big way. Okay, so then for this, when I rasterize this triangle for this pixel, maybe they're mapping to the very tiny region. This actually the texture map. So this actually each individual texture, the pixel in the 2D texture map. Then when I rasterize this triangle, this rectangular shape of pixel may be mapping to the very small region, right? Since I zoomed the triangle a lot, right? So then basically in this case the mapping region corresponding to the one pixel here, actually the mapping to the sub region of the texture region. Suppose that actually you can see that actually this actually the textile region in the 2D map. So this one we call it this effect, this issue happen when you magnify the triangle a lot, and then we have to say that it's actually oversampling issue. In other words, we actually have some sort of information, texture information in each pixel, but in other words, we need to sample a lot of we need to request more information compared to the content stored in the texture map. So that's why we call this oversampling issue. The other one is that I draw the triangle very small. In other words, in this case, I draw the triangle like this, right? Somehow I look at the triangle very far away. Then here I need to compute I need to compute color for this pixel, and this one maybe this region may be mapping to the very large space in the texture space. And this is happen when you look at the triangle zoom out. So actually this happen in the minification cases, and this undersampling, right? So basically, there, even though I had a lot of the texture information here, but I can only use one pixel here, right? So in other words, out of this many texture information, I can give it only the one texture. So this is actually undersampling issue. This is actually oversampling, undersampling. Actually, they're quite commonly appearing. So we need to have the very good and we need to have a very good techniques for addressing these issues. First of all, let's talk about the oversampling issue here. This case, somehow my texture region, so pixel of triangle pixel of the pixel mapping to the one triangle mapping to a very small region in the texture map. Oversampling issue. Here now this region here. So in other words, since actually they're looking at this rectangle, some of this arbitrary shape takes a lot of time. We usually look at we usually take this point sampling, right? Suppose that this actual texture the texture pixel, the center of the pixel, and it has this color, this color, and then some of the texture region that are mapping to the pixel in the screen space, and then I picked the sample. Basically, I need to get a texture color for that kind of the sampling point. And how can you compute out of the nearby actual texture color? How can you compute the color for this one? One simple method is the nearest neighbor search. Nearest neighbor. In other words, for this one, I identified what are the actual nearest neighbor texture information, right? At that case, for this pixel, actually nearest neighbor the texture information. So I used this color for this one, right? So if I actually visualize for all the other regions, and for this region, so this texture has is the actual nearest neighbor. So we should use this color. But when you approach this boundary, we suddenly actually see that its nearest neighbor texture is this one, right? For that one, right? So for that region, we use this color. We can use this color and that color in this case. You can see that it's very simple, but when you cross the boundary, then you can see this sudden color change, right? That's the issues of the nearest neighbor approach. Then maybe in this case actually along the boundary we change the color suddenly, right? We don't want that. So another approach is that we want to smoothly change this color, right? So along that line, we can use this bilinear interpolation. It means that we perform the linear interpolation in a twice in a bidirectional cases. Suppose that this is actually the texture color here, C0, C1, C2, and C3, and so on. And then I want to know the color information. And basically, and then this actually this coordinate for this one x0, y0, for this one x1, y1, and then I need to get a texture color for that location that has x and y. Then how can you do that? One simple approach is that I know the color information here and there. Basically, I know the color information here and there, right? So that I can measure what's the actual distance from here to there, right? Let's say this alpha, and this might be 1 minus alpha, right? And then based on this one, I can do the linear interpolation out of these two color information for then can compute the color for here, right? By blending alpha and 1 minus alpha, right? That's a linear interpolation. I can compute color there. Also, I can do the same approach applying to the here and there. Also, I can compute color there, right? So I do the linear interpolation there along this x coordinate, and then I get color here and there, and then I do another linear interpolation along this y directions. So also I know that this might be the beta and 1 minus beta. Then I can actually I perform the linear interpolation from to there. I actually as an amount of the beta and 1 minus beta, something like that. Then I can compute the color up there. So basically, if I actually explain if I'm showing the equation that I talked about the bilinear interpolation, I can get this kind of information. You can actually find out this equation based on this concept. So by using the bilinear interpolation, we can get a very smooth the color change, right? Maybe this could be better than just using this kind of color, right? But it may be a little more complicated. In other words, it may require more computations, right? Which may be a little bit burden to the processor, right? This is also one of the reasons why I have to use the GPU. So there are for each so in other words, when you rasterizing this triangle, every pixel we have to do this operation, right? So there so that when you usually we have to use it's better to use the bilinear interpolation. So in that case, we need to use a lot of the multiplication and addition, something like that. So that's why actually that's one of the reasons why we are having the GPU that accelerating this kind of operation. This actually visual comparison. Actually, let me show some of the demo here. I think that this texture filter demo is available, available from our course homepage. If you click if you run this texture filter one, then you can have this one. So you can change it here. So I think that we have to use this one. So here, if you click the H, then you can see that there are some of there available key map here. But I remember this key map here. For this case actually, we zooming in. This case, we actually zooming in the triangle a lot, right? So that's basically this is actually oversampling issue. So that actually is a texture. There are not many the texture pixel, right? So actually across this region, you see the texture resolution, right? So that's the bad. So in this case, I think I used the nearest neighbor search. Nearest neighbor. So here actually the filter is that this nearest neighbor one. And then if I choose the linear, in other words, this like bilinear, then you can see that the pixel change the color change smoothly, right? That's the main benefit of using this bilinear interpolation. So it looks better, right? It looks more smooth. So when I change it N and N, and so on, you can see that, right? So in this case, original texture is like this. It's very low resolution, and then again, when you zooming in this triangle a lot, you can see that there actually oversampling issue happen. You can see that this texture boundary. So when you change the linear one, in other words, I change the magnification filter, then handling oversampling is linear. You can see that that's actually the filter label, but basically we are using bilinear interpolation that I talked about before. We can get this smooth information, smooth and color change. But you can see that actually it's smooth, it's nice, but sometimes some of you may feel that it's overly smooth, right? Which is bad, right? Also, that's also the issue of this simple bilinear interpolation, right? So in other cases, we need to maintain original high frequency information. There should be some sort of important edges in the texture map, right? But when you do the bilinear interpolation, maybe we are actually smoothing out that edge information, right? That's not the desirable one. So somehow we need to have some sort of the technique that maintain the original edge information. In other words, high frequency information, while actually the smoothing out some of these smooth regions. So it's a little bit difficult issue. So that's why there are a lot of research still going on along this line. So if you're interested, you can also look at this one. And related keyword is the filtering or the reconstruction or the sampling, that kind of one. Okay. I'll talk about the other issues here. Now let me talk about the undersampling issue. Undersampling issue is that, as I showed before here, somehow we look at the triangle in a very far away location. So one pixel here in the screen space mapping to a lot of the pixel region here. That's the undersampling issue. And then actually it turns out it's much more complicated complicated issue. So in this case, we are looking at the triangle very far away, right? So triangle very small. But somehow for that one, maybe at worst case, actually that pixel will be mapping to the whole region of the original texture. There are a lot of texture information, but we can use only one color, right? So that's why you can see that there are some of a very odd pattern here, right? That basically it's not the pattern of the original texture map, right? So you can see in this case some of these details in texture actually in this case the details of this texture one is that there are this brick, right? This actually red color. Also there are actually some sort of white material between the bricks, right? So basically, there's sometimes actually we see the red one. Sometimes we see this white color. So this kind of the details actually tend to pop here and there. It also disappear and appear and so on. So that's why it makes the very odd patterns. Actually, this white substance known as the mortar actually. Basically, the white color appearing here and there, but you can see that in a some particular pattern, right? Which is pretty bad, right? So as I mentioned before, the high frequency details. In other words, some of I didn't really define what's the high frequency details, but you can see this actually the edge or the boundary, something like that, lead to the strange pattern. In other words, this white color along here, their color change a lot, right? Drastically, right? It makes high frequency the color change, and that lead to the very strange pattern here. That's known as aliasing actually. So this issue is actually related to some of the signal processing theory, but I'm not going to talk about all that kind of theory. But actually, when you're rasterizing this triangle, then we actually somehow even though actually there are a lot of information, somehow we actually choose a particular the texture color here. I mean, even though there are maybe 10 one, we only pick only the one of them in a particular way. So that's why that makes the undersampling, which lead to the aliasing issue. So that's why it makes the very odd pattern. That basically that's how it goes there. So basically, we don't want that kind of this aliasing issue. So to avoid the aliasing issue, so basically the main setting is that here some of the triangle, when you rasterize the triangle, one pixel. Here I visualize one pixel of the triangle in the screen space mapping to this large area in the texture one. So suppose there are a lot of triangles, a lot of texture color, right? But we can only use one color. The question is that what is actually the representative color, texture color for that region, right? But one of simple approach is that we can actually look at all the texture color within the region, and then we can maybe compute the average color, right? We can do that. So basically, that's what we are doing here. Is that to avoid aliasing, we need to do the free filter. So we can look at all the texture color here. We can compute the average, but it may take a lot of time. So in other words, we want to pre-compute that process, right? That's why we call it free filter the texture, remove the high frequency. So basically, there are a lot of the information here, but when you do the averaging out, in other words, we actually remove the high frequency, right? That's the computing the average is basically nothing but like this. So if we do that, you can see that actually it looks much better than compared to this one, right? You can see that actually for here we got the very odd pattern here, but now if we do the proper filtering, then it can remove the aliasing. So in this case, actually we call this actually spatial filtering. Since we actually do this kind of the filter in the 2D space, in the texture space, spatial filtering. So if we do the filter, it will actually improve quality a lot. Somehow it actually avoid this aliasing. There are a lot of research going on. There are a lot of theory, but I skipped all those parts. But I wanted to try to explain this idea in a high level. So in other words, the free filtering essentially, you can treat the free filtering as the averaging out. Free filtering is essentially spatial integration over the texture. In other words, we integrate all the color value, right? And then we compute the average. Integrating on the fly expensive, right? Since we have to look at so many texture color information. So we need to do the integration in the pre-process. Along that line, actually the beam mapping actually very commonly used. MIP BIP is the acronym for the Latin phrase multium in parvo. It means that many in one place. So basically the beam map looking like this. This is the original texture map at high level. We actually for the original texture map, we reduce down its resolution into half. So we reduce the width and height in half and into half and half. And then at that case is 2 by 2 pixel mapping to the 1 pixel here, right? so that actually for that pixel, we averaging out the color of this 2x2 region. We actually compute the average color of 2x2 and then store there, right? So that way we actually reduce the resolution into half, and then we keep doing that. So actually so there are actually many things in one is the min map, right? So that's why we call this actually MIP, and the technique that using this MIP is min mapping. So here also this code also actually called as an image pyramid. Looks like pyramid, right? And each level is pre-filtered version of the level below here. In other words, below here is that you go to that high resolution, and then we actually we sample this one in there by reducing that resolution into half. We keep doing that. That's actually min mapping. And then when you actually rasterize this triangle, so somehow in this case, this region, this pixel, if we mapping this pixel into this region, we actually maybe this one pixel mapping to a lot of texture here, right? It's not good, right? So somehow across these different levels, maybe there is this one, then this one pixel here, this triangle mapping to maybe maybe one or two the texture information, right? Texel, then we can use that texture. Then basically that texture actually the kind of the average information average information onto this corresponding region in the original one. So basically by using this one, we can effectively perform the averaging operation in a pre-process at one time. We can only access only the one or a few the texture information, and then we can compute this averaging the color in an efficient way. So in other words, we pre-compute this information at one time. We just using the data structure. So actually, we achieve the very fast runtime performance while maintaining good rendering quality. That's the main idea of the min mapping actually. So then you can see that actually on top of the original texture, we are using the additional one, right? So basically here given this original one, we actually reduced half and half in width and height, right? And then we used actually 104 additional one, and then if we keep doing that, it turns out that actually it's required that the total actually the memory space is actually 4/3. In other words, we used the 33% more. It required that this actually boils down to 33% of the original data structure. 33%. This actually also visualize here also how we can store the min maps into the memory. So basically here I'm showing the 10 different min map level here. Original one, which is half and half, and then actually this texture consists of RGB, right? And then if we actually reorganize this texture into this one, for original one we store RGB, RGB, and then we actually get the additional one, right? And then we also we also do the same operation here and there. Then we can use this region in a compact way. Then you can see there also it actually illustrates the 33% of the overhead. Basically, we are using this actually 1/3 of this original actually the texture map. It also illustrates the 1/3 overhead by looking at this one. And I think that I already talked about how we can find the proper the min map level. So I don't want to show the exact equation. The main idea is that for this, when you rasterize this one triangle, this pixel region should be mapping to the one pixel space here, right? One pixel width. So maybe there are certain equations to do that, but I will skip that the low level details. But I hope that you can understand high level idea. Okay, so now I talked about the theoretical concept. Now I'd like to talk about how we can utilizing this texture filter in OpenGL. So first of all, we need to create textures min map, right? But OpenGL already providing that. I mean, there are many graphics library already have that some of the function, right? here in OpenGL we can use the GLU build 2D min map. There are a lot of some of the actually the parameter. So if you want to know the parameter of this one, I recommend you to Google it. And then for the filtering, you can use you can call this function GL text parameter, and then you can specify what kind of the parameter you want to change. Here GL texture 2D, and you are using the 2D texture map. Actually, later I'll talk about there are even the 3D texture map. So I specify the 2D texture, and I'd like to talk about the texture, the filter related to this magnification, and I specify the filter there. And filter options there are a lot of them. Nearest neighbor, nearest also the linear, and also there are another one. Basically the GL texture min filter. This actually this relates to this minification issue over undersampling. And then for this one also there are also many the parameter. It's not really important to know every details here. The main thing is that there also for this you can use some of them, the min map, but there are also some other actually the term the GL linear, min map linear. It indicates that the linear is even the interlevel. In other words, here so far I just mentioned that for this pixel I picked only the one min map level, right? But why not just using the one map? I mean we can also using we can pick the two layer, and then we can also averaging out, right? So we can do even the linear along the min map space, right? So that's why we can also pick we can call the linear or the nearest into the interlevel, and then here this intra level is within actually the one layer of the min map. We can use the linear and the linear also this nearest. So obviously, when you are using the GL linear, min map linear may require the more computation when you perform the texture mapping. But anyway, it may give you the best quality. So, but before I finish up, I'd like to also I will show that I will actually visualize this in the demo. Here, basically now we look at this region. So this region actually you can might be whether you are doing this operation here, then some of the actually color actually it changes a lot, right? It looks very odd, right? For this region, but when I use the here linear min map, if I use min map, then you can see that the color changes very smoothly, right? It looks better, right? This bad. Here actually I don't use min map. I use min map. It looks better in this region, right? That's the main benefit of using the min map. Okay, so far I talked about the texture mapping overview. Also, some of the texture filtering issue related to the oversampling and undersampling. And next time I will talk about actually some of the different applications of texture mapping. Basically, the concept of texture mapping is very simple today. While there are some of the issues of using it, but also that we can apply there are many actually diverse set of application of the texture mapping. Actually, one of the main idea of the using rasterization for achieving realistic looking is nothing but using the texture map in a very different setting. I will talk about that one, and then once we are done, I will move on to the ray tracing. So again, this is the regular homework. Go over your next lecture slide so that you can actually be ready for taking the next lecture material. Also watch the figure Asia video and submit your summary before every Monday class. But also there actually I'll talk about last basically I actually mentioned that there are certain there will be last submission deadline. So I recommend you to look at the KLMS, see that deadline, and submit the question 2 times during the whole semester. If you didn't submit the questions, I recommend you to do that through the Google form. That's it. Thanks so much. Bye.